So I'm going to talk today about how we can accelerate the process of building machine learning models by changing the way that we create and manage training data for them. And the motivation at a very high level is that training data is often the key ingredient, and increasingly the key bottleneck in building machine learning pipelines. But for something that's such a key ingredient, it's increasingly, largely created and managed in almost entirely manual or ad hoc ways. And so the research question that a lot of the work that we've done on the Stanford side is anchored around is a simple one. Can we add a little bit of mathematical and system structure to the way that people in the real world build and manage their training sets? And can we use this to lead into new ways of interacting with the machine learning stack? So I'll start with a running example. I want to try to stay somewhat agnostic to what the particular application is, because Snorkel is really somewhat orthogonal or the systems I'll talk about are about training data for machine learning models and what those models are. We can get into the definitions, but we approach it at a very high level. But I'll ground it in an example that I'm excited about these days. So despite some journal rejections, it is at least posted, and I'm quite excited about this radiology application we've been working on with the Stanford hospital system and a couple of other local systems we're rolling out for deployment. The motivation really concretely is we're trying to do case prioritization. So no nonsense about replacing radiologists tomorrow, all about assistance through prioritization and triaging. So simple way that an ML model fits into the stack. We have a chest x-ray, and we just want to train a model to do binary classification. This is kind of the simplest version, just a supervised learning problem. And again, this can be a big help, even in the short term, in terms of actually affecting how we prioritize cases to be read, say find emergent ones and get them to doctors sooner. So the standard way you'd go about this kind of a pipeline is kind of converged today. I'm definitely glossing over details and complexities where there's a lot of cool work going on. But to a first order abstraction, you start with unlabeled data. In this case, I'll mention, this becomes relevant later, that it's multimodal, in that it's not just the images, it's also metadata, blobs of text, et cetera, along with it. We pay, or in our case, beg our kindly radiology collaborators to spend a bunch of time labeling the training set, looking at the images and labeling normal, abnormal, et cetera. And then, they built a model. In this case, it was a ResNet. This is a classification model to actually train based on that labeled data. So the interesting thing, first of all, is that when I entered grad school, say 5-ish years ago, I'd kind of block out the exact number, but somewhere thereabouts, this would be sort of where we were going to research, right? How do you do feature engineering for these models? How do you actually build the algorithms, et cetera? Today, it's almost commodity, right? I know that's a bit of an out there, and I'm intending that as a provocative statement, but it's increasingly true that if you want to build one of these state-of-the-art image classification models, you just it's like 2 lines of Python if you set it up right, using Python or PyTorch or TensorFlow or MXNet or any of the other models. And in this case, our radiology collaborators really only took about 2 or 3 days, modulo the overnight training time, to get a reasonable solution. And actually, then when they went back and they looked at basically 5+ years of deep learning architecture progress in imaging, from trying AlexNet all the way up to ResNet and DenseNet for those who are familiar with these architecture names, there was only about a 1 point difference in terms of the end ROC AUC predictive accuracy score. So this is a common theme that we're seeing in a lot of settings where model development is actually radically easier than it was before, and it's not really the thing that's the key differentiator, the key bottleneck in terms of getting something to work. On the other hand, I'm sure you could guess where the punchline was coming in at. They spent about 8 person months, even on this simple binary chest x-ray triage problem, just labeling the training set. And interestingly enough, when we actually look at the difference between, say, a couple thousand labeled data points and then the full 100K plus labeled training data points they produced after 8 months, there's about an order of magnitude larger differential than the choice of the fancy model architecture. Similarly, when we actually stepped in and tried to improve the quality of the training labels, and I'll get into much more depth about what I mean by quality, it was a similar sort of order of magnitude larger effect on the end score. So again, in a large variety of settings, not all, but many ones that we care about, training data is the key bottleneck and the key differentiator of how this end performance, or how this end model performs. So just to make this a little bit more concrete, what we're motivated by, what we're trying to sort of build around, are 3 challenges of training data management most broadly. So not just labeling the data, but managing it in general. The first is that volume is critical, as I went over, but it's often incredibly slow and expensive to get the volume you need. right? Most problems are not actually just sending data out to Turkers, where you can pay kind of lower prices, but they're asking people like radiologists or cybersecurity analysts or et cetera, who have domain expertise and often need to be on-prem to actually label the data by hand over months or years and at great cost. Quality is critical, but it's challenging to assess. Almost sounds kind of circular, and I'll get into some of the interesting theoretical questions there. And also something that's often, I think, massively underpriced in academic ML is that flexibility is critical, right? So the traditional conception, it's a great abstraction, but the traditional conception of training data is just a bunch of labeled XY pairs, chest X-rays and a label, normal, abnormal, and it's just completely static. But in any real-world condition, or almost any real-world condition, this changes, and then you need to update your training set, which usually means just throw it out and start over again. So just a really simple example here is, we had normal, abnormal. That was the schema we were training the model for. And then the hospitalist we were piloting with came back and said, actually, we want more buckets, right? We want to break abnormal into emergency or non-emergency, right? And we had no real good way, and in general, people don't have a good good way to handle this other than just throw out the training labels, start over again. And this is ditto if you have a model as part of a broader pipeline and you have upstream or downstream changes. If I've actually had a 3-star general who was visiting Stanford talk about the problem of schema lock-in, of having to spend a lot of money on training data and then getting locked into a schema. The data distribution changes, the devices and say a medical imaging setting change, really anything. There's not really a lot of flexibility in the paradigm of just a big labeled training set or hand-labeled training set. So the research that we do at the lab at Stanford that I've worked on for the last 5 years is building systems that basically try to address these challenges or fulfill these desiderata using kind of a 3-step high-level blueprint. So the first is that we want to let users specify training sets in higher level and programmatic ways rather than by hand. The second is we want to do something in a principled way to clean and integrate this kind of higher level, messier input. And then finally, we want to be able to plug this into the machine learning stack where there's been so much progress and investment and tooling in the last 5-10 years. And we found that by following this kind of blueprint, we can actually get new ways to program or specify machine learning models that actually lead to development of end-to-end pipelines in hours or days rather than months or years. So in this talk specifically, I'm going to talk about 3 systems that support and accelerate critical steps of the training data management pipeline more broadly. So the first one, and I'll be focusing on supervised learning, right? So this is in contrast to, say, Ray that we just saw, where it's in some ways a broader, setup of reinforcement learning. This is just your sort of vanilla bread and butter ML pipeline, where, I would argue from experience is what the bulk of sort of production applications today run on. Just, learn to classify this with a certain label or a scalar value. So labeling is really important here, obviously. That's a central activity. I'm also going to talk about something called data augmentation. If you look at image applications and increasingly other modalities, this is the idea that you can kind of artificially boost the size of your training set by perturbing or transforming data points, like rotating all your images randomly. It's actually kind of an interesting way, a new way of injecting invariances into your, or knowledge of invariances into your model via the training data. And then I'll also talk briefly about multitask supervision, which is just kind of revisiting the old idea of wanting to transfer information between models and actually train one model that does multiple things to get more from less samples or less signal. And I'll spend the bulk of the time talking about the system that I've worked on over the last 5 years at Stanford called Snorkel. This is an open source system for trying to let users programmatically label training data, or rather to support that emerging process that we see out there in the world. And then I'll just talk briefly about a system for sort of also supporting data augmentation and letting people put in operators about transformations and then tune that automatically. And then also a recent system we've been working on, actually that just got a state-of-the-art on a multitask learning benchmark called Snorkel Metal, which extends Snorkel into the setting where you have multiple tasks you care about that you want to kind of handle jointly. And also mention deployments that we've used to both motivate and validate these systems, in particular Snorkel in industry, government, and science and medicine. So I'll start with Snorkel. And again, the problem, also again, please just stop me if you want to ask questions. So the problem, and apologies in advance for being congested. Actually, the whole reason for the name Snorkel is that I had proposed it, and then I thought, I had a cold at the time, and I was like, I sound god-awful saying that out loud. And then at which point my advisor said, and I will veto any other name because I want you to have to stand in front of people and say Snorkel with a cold and sound ridiculous. So here I am. Okay, the problem again motivating this is that hand labeling training data, that critical sort of step in the process of building an end-to-end ML pipeline is really slow and expensive, and it's static, right, in real-world settings. That's often very prohibitive. And so the simple idea that we're motivated by here is trying to enable users to label training data programmatically rather than by hand. And the key technical idea undergirding this is that we're going to view training sets not as this sort of perfect noiseless object that we download from the internet and then get to work training our fancy model architecture, but rather as a noisy programmatic process itself that we can model and denoise. And so we operationalize this in three main steps. The first is that rather than having users hand label data, we have them write what we call labeling functions. These are very semantically poor basic objects, just at the basic level that we handle them. They're just black box functions that take in an unlabeled data point and either abstain or apply a label. In the second step, we work on trying to clean and combine these labels, basically take the output of the different labeling functions and learn how much to trust each of the labeling functions, which labeling functions are correlated, and therefore how should we reweight and combine their outputs. And then the output we call sometimes a training database. It stores a bunch of labels as well as the lineage or the provenance from the sources they come from and their quality. And then we can just basically plug this into PyTorch, TensorFlow, et cetera. Yes?
Kind of understand how you can find correlated, but how would you clean your labeling function if you don't have any source of?
That's exactly the interesting question. So I'll get into that, and if I don't give a clear answer, I'll bring it up again. Yes?
When you write labeling functions, you're writing multiple labeling functions for each example, let's say. So for one example that comes in, you could potentially get back n number of potential labels, zeros or ones, let's say, a binary, and then you're saying that the Snorkel system makes a decision on which is the best label to apply for that example?
Exactly. So, just to sort of get right-size the order of magnitude, it's like, maybe a domain expert writes, 20 labeling functions, right? And so they can abstain, but you might have 5, 10 different labels that conflict and disagree and are correlated for any data point. And we're looking, how do we reweight and combine them, right? In the simplest form, it's just, I want to take a weighted majority vote, basically break ties, figure out which ones to trust. Yes?
I don't know if currently or maybe previously, have you had a blend of approaches where you've mentioned you can abstain a label, maybe have an image that doesn't get any label applied to it after all these labeling functions? In that case, would that be kind of manually labeled as if it would be in the previous process, and then you would use like a blend of the two? Yeah,
so that's great. And in general, the idea of blending different orthogonal approaches is a broader question that we could discuss. It's very interesting. We've applied Snorkel, we think of as weak supervision, along with things like semi-supervised learning. Active learning is another orthogonal thing that you can do in this framework. There's lots of cool things you can, just at a high level data, blending approaches together. This includes strong supervision, right? You can dump in labels if you have them. So I'll emphasize a lot that Snorkel doesn't require any hand-labeled training data. Actually, there it is. That's kind of the provocative and interesting bit on the theoretical and academic side, and it ends up being very useful in practice when it's very expensive to provide labels. But again, if you have them, you can dump them in. In fact, a bunch of labels, especially ones you don't know if you should trust, could be a labeling function. The second thing you brought up is, what if all the labeling functions abstain? And that's where we rely on this final model to try to generalize a bit, and I'll get into that as well. So let me proceed now, and then I'm going to kind of go into each of these buckets, and then we should revisit some of these questions, because some of them are very interesting and deep. So I'll mention just briefly, we've deployed Snorkel a lot over the last 4 years. It's open source. A lot of these, it's kind of got there's an artifact online at snorkel.stanford.edu. You can check it out along with the papers and stuff. It's sort of a version that we had from about 2 years ago based around a text extraction type problems. Then we've deployed various versions of it in science and medicine with the Stanford hospital system and the VA system and a bunch of other partner labs we've collaborated with. In industry, it's being used in production at Google and Facebook and Intel. Actually, I'm not sure, Facebook, POC, Google and Intel, Microsoft, Ant Financial, IBM, and some others that have been longtime collaborators, and also in some government settings, like it's being deployed in the DARPA MEMEX pipeline at the DOJ for pulling out data from online pages to fight anti-human trafficking, so part of that pipeline, amongst others. And in many of these cases, the sort of bullet point takeaway is that we can actually take an end-to-end process from sort of starting a new problem to training a model that used to be, if you actually counted all of the steps, person months or longer, and turn it into something that's more in the order of hours or days of something that looks more like programming. So now I'll go through the 3 steps and give a little bit more detail. So the first step is this idea of a labeling function. So at the most abstract level, it's just a function that maps from your input data point to your output space where you're trying to make predictions in, or abstain. Again, abstain just means I don't know, and I'll just denote it by a 0 here. And so it's just meant to be a simple abstraction for expressing domain expertise or other sort of noisy sources of data. And again, it's very semantically poor. We started thinking, okay, maybe we'll do something with first-order logic or some kind of like declarative query language or et cetera. It's still of interest, but we really just said, okay, we want to let the developer be creative and kind of just dump in whatever signal they have and then try to deal with that in a simple, basic way. So it's a really simple function. And I'll give an example, right? So imagine that we have the text portion of one of those case studies from the hospital PACS picture archiving system. And here is a labeling function actually written by a clinical radiology fellow with some basic Python knowledge that was a user and collaborator on this project. And this one just says, look for the prefix pneumo in the text, just a pattern matching function. And if you see it, say abnormal. So that's what I'll denote by this red X. So labeling functions, again, are just really simple user-defined functions. Again, the intuition is we'd like to just express something that's in the labeler's head in a more information-dense way than just sort of, yes, no labels over a huge set. Of course, these labeling functions can be wrong. This one obviously misses the negation, outputs the wrong answer. And again, the key that I'll get into in the next step of the pipeline is that labeling functions can be noisy. They can actually be noisy to varying unknown degrees. And if we have a couple of them that are sufficiently uncorrelated, we can handle this. But before diving in there, I'll just mention that the intention with these labeling functions was to sort of provide a simple abstraction and framework for a lot of what's often been called weak supervision techniques that are used in practice, often in creative but ad hoc ways. So this includes pattern matching to label data. This includes something that's called distant supervision in the natural language processing community. This is, at a rough level, the idea that you take an existing knowledge base and map it to your data to label it. Here, as a simple example, and I'll note these are all labeling functions that were written as part of that radiology project with the clinical fellow. This one just says, look, take an online ontology from the NIH of disease phrases, cross it with the words in the blob that the nurse or doctor dictated, and if there's an overlap, return abnormal. Right? So you can imagine this one would be very high coverage. It doesn't abstain that often, kind of low signal, but still has something useful. We can express domain heuristics, like if the report, the text along with it is really short, it's probably not an emergency. Those 3 were over the text portion. We can also let people write labeling functions or express their domain knowledge over more complex modalities. So I can get more in depth later on in the questions, but we had a paper where we were doing, first we just applied a lot of off-the-shelf unsupervised algorithms to images, and that let users write labeling functions over those sort of building blocks or primitives. So for example, we can write one that says, okay, if this sort of circle detector finds a circle with a large radius in the image, labeled abnormal. Get just a rough way of expressing the intuition. If there's a big blob in the image, it's probably bad. And again, we can take crowdsourced labels. We can take other models that might be low coverage or brittle or biased, dump them in as labeling functions. And the result is that rather than having 100,000 or 10 million hand-labeled examples, again, that we pretty much have to throw out if something changes or really if there's any question about an issue with them, we have supervision in the form of code. Right? And it comes with all the resulting benefits of being more interpretable, more modifiable, much faster to write. But of course, the trade-off is that it's a very, very messy type of supervision. So just to give a sense of those challenges more concretely, imagine we have this report again. Here are 3 of those labeling functions. Challenge number 1 is that these labeling functions have different accuracies. Right? And they'll often disagree with each other. And here, if we even just tried to take, say, a majority vote of their labels, we would get the wrong answer. The second problem is that they can have correlations that are kind of subtle. So here, for example, just to dive in, this one is looking for the word pneumothorax, basically, a type of disease. That's pretty much where my medical knowledge ends. Here, we're just saying, okay, cross-check with this disease ontology. You can imagine that if this ontology contains pneumothorax, then there's basically a logical relation between these two. And if you counted them as sort of uncorrelated sources of signal, you'd be double counting their votes. And finally, we have to try to handle these things without any ground truth. Again, we may have it. I can get into that. It's fairly easy to incorporate, but the context we consider is that we just have these noisy labels. We don't have a large ground truth labeled set, right? Otherwise, we would just use that to train our model in the first place. So we view this as a new type of data cleaning and integration problem. And the next step is basically how we solve this. And the question to anchor on here is how we do this without ground truth labels. So this is where I'm going to skip through some stuff that I get very excited about, but most other people in the world don't. And I can always circle back to it if we actually want to step through it. But jokes aside, it's honest. I think it's more interesting just to talk high level and then have discussions based off of that. So let's see. I'll give the high level sketch. Is that we view, we represent this kind of black box set of labeling functions and the noisy labels they output. And there, again, there's arbitrary logic within them as a really simple generative process where there's some true unobserved variable or a latent variable. That's the true label that we don't see. And then some observed random variables corresponding to the output labels of the labeling functions. Our goal is to recover some parameters that describe, okay, what accuracy do these observed labels correspond to the true label. I'll talk about here, well, I guess I'm going to skip through most of this, but I'm going to talk about just a single parameter, just, okay, we're trying to learn one accuracy for each labeling function. We can do much more interesting extensions of that. For example, we might want to learn that different labeling functions are good in different parts of the data space, right? We might want to learn data conditional accuracies. We'll also include pairwise dependencies. And in this brief part that I'll skip through, we assume that we kind of know these edges, but we've done a lot of work, hopefully 2 papers soon, on statistical approaches to learning those correlations. Again, the key question is here, how do we learn the model? How do we learn the accuracies and the correlations of these labeling functions, these really messy black box objects, under this simple model of the process, but when we don't actually observe the ground truth label? And there's a lot of prior work on this, a lot of it from the crowdsourcing community. I'm going to skip by this. There's lots online we have about this. This is the main thing I'll present at this point, which is that the key idea that we anchor around here, and this is something that is a kind of an old idea at the highest level, is that we want to learn from the agreements and disagreements between the labeling functions, and only learn from that, right? So we don't know what, if we knew the ground truth label, we could just count, right? I want to know how accurate this labeling function is. I'll just count up how many times it's right and how many times it's wrong, right? But because we don't have the ground truth label, we're just looking at the record of how they agree and disagree with each other. And actually from that, we can provably recover under basic settings the accuracies and the correlations of these labeling functions. So I'm going to skip by this, but I can go back. There's a new approach that we recently presented on how to do this. But I'll kind of sketch the ending point here. And again, I'm happy to loop back afterwards, or this is all online. The result is that we get a problem, and just for some of you, this might kind of look familiar in that it kind of looks like a matrix completion problem, which has been a lot of, it's not a nice, convex problem. It's kind of nasty in its own right, but there's been a lot of work, both theoretically and empirically, on how to solve this kind of a thing, right? Think like Netflix challenge, that kind of line of work. So one reason it's nice is that we can actually solve this nasty problem of learning the accuracies and the correlations just using basic stochastic gradient descent in a form that we kind of know. It's also scalable. This is just, I'll mention briefly, but if n is the number of unlabeled data points that we have, so the number of, basically in the radiology example, say the number of case studies that we have that we apply these labeling functions to, and d is the number of roughly labeling functions or correlations between them. So think like 20, 30, something on that order. I guess this doesn't make sense with the part that I skipped over so much, but basically we have these much smaller matrices that we're actually optimizing over. So basically first we compute the agreements and disagreements, which is this sigma O, which is just matrix algebra, and that's fairly fast. And then all the ML kind of optimization components of this are really over these tiny matrices. relatively speaking. And then finally, we actually show some theoretical guarantees that we can provide for these settings. And I'll just give a sketch of this. This will be the only part of the theoretical jibber jabber that I go into here. But the basic sketch of the result that we drive towards in some of the sort of theory papers here is that if we have n of these unlabeled data points, so again just like the unlabeled case studies on the PAC system at the hospital, or the number of documents we're trying to classify that don't have labels, for example. And then we assume, second, that we have a set of labeling functions that are on average better than random, right? So if we assume that if there are 11 labeling functions, the subject matter expert or user writes, that just 6 of them are better than 50% accurate, right, at least. And for those that are familiar with these types of problems, this is just a way of breaking some final sign symmetry that you have to deal with. And finally, this sounds kind of tangled, but this actually has also maps back to kind of a real-world question for developers in this kind of a pipeline. So the statement is that we also assume that there's a sufficiently sparse dependency structure between the labeling functions. All this means is the following. Here, I'll just sketch some intuition. So you could imagine that this graph, bless you, would look like, okay, every labeling function has a correlation between pairwise. A really bad, extreme version of this would be, imagine if you just dumped in identical copies of labeling functions, right? So you really only have one source of signal, but you just have 10 copies of it or something. You would guess that we can't really do anything there, right? And that's correct, right? Snorkel is not going to learn anything, at least in this part of the pipeline. On the other hand, if you have a bunch of, this model would correspond to labeling functions that are completely conditionally independent, meaning they're completely uncorrelated in their errors. This is a model people often use to model crowd workers, right? They're just sitting off in their own rooms, colluding or sharing notes at all. In this case, where they really are uncorrelated signals, this is, lots of work has been done on this, whether it's in finance or crowdsourcing or whatever, you'd guess this would be good. So the question we ran into with users was, okay, well, how do we know where we are? And what is enough? When are we okay in that we have enough uncorrelated signal to do something? Again, just intuitively, you need to have some independent views of the problem to be able to do anything in this kind of modeling procedure. So we provide a deterministic test for this that basically either tells the user, almost like a compiler check, you have diverse enough labeling functions or you don't. You better come back and get some more sources of signal. And then what we show is that actually the estimation error of recovering these accuracies and correlations decreases asymptotically with the more unlabeled data we put in, at the same asymptotic rate as you traditionally show for the supervised learning setting. So at a high level, this says, A, we actually have something that we have theoretical reason to believe will actually converge, unlike some settings where you're playing tricks to label data. And second, that actually we should benefit, theory says that we should benefit from dumping in more unlabeled data and running it through the labeling functions. Simple takeaways, but I'll get back to some empirical results that follow from this. Okay, so anyway, just the recap, and again, happy to dive in more detail about the actual approach that I skipped over, but we have these labeling functions, these kind of noisy little programs, black boxes that just output messy labels. We model them as a simple process where they have accuracies and potential correlations. We show that we can solve this using a matrix completion style problem that we kind of know how to handle. And then given that, we can use basic techniques just to get a probabilistic label, basically a way to reweight and combine the labeling functions labels. Yes?
Is there an optimum number of independent labeling functions that you strive for?
It's a great question. The more, the better, actually. So the more, if you just keep throwing independent labeling functions, by a kind of law of large numbers type intuition, you could just take a majority vote. And we actually have a little treatment of that of, if you have 20 or 30 labeling functions, Snorkel gives you a much bigger boost over some simpler approach, say just majority voting. If you had like thousands of labeling functions, you could just kind of add them up, and if they're really uncorrelated, simple stuff works. But it's a great question. The cool thing is that you don't need them to be really accurate. It's actually more important to have uncorrelated kind of diverse sources of signals than it is important to have like really high accuracy. You could have a whole bunch of labeling functions that are 60% accurate, but if they're truly uncorrelated, this can work, right? Yes?
was wondering if you guys have incorporated an iterative approach here, because you're learning a lot about what are potentially good and bad labeling functions.
Yes.
So I'm curious, like something like Weasel, like weekly active supervised learning, or
Is that an acronym you just made up, or is that an existing one?
actually it's a thing that
I'm ready to be impressed.
one of my buddies knows you from Stanford, but we wrote something called Weasel for a company that we worked at.
Oh, really cool.
And we leveraged a lot of your work on the first pass, but the hack that we found was that we learned a lot about our labeling functions.
Yeah,
We
yeah.
could improve independent labeling functions by just allowing our users to iterate. And so anyway, I was wondering if you guys have incorporated some of that yet or not.
Yeah, no, that's awesome, and I'd love to talk afterwards. I'll try to pounce afterwards. Mostly because that's an amazing acronym.
Yeah, we're pretty stoked.
Yeah.
And we have it on PIP, the public index already.
I almost made a stoat joke there. That would have been really, truly terrible. But we've done that. I mean, one thing that I guess doesn't come out well in this version of the talk is that this is always an iterative process, right? We're in a sense that, phrased another way, the goal of this project was to support what we saw as an emerging development process, right? We saw people kind of hacking together training sets from different sources, different qualities of label sets. We saw ourselves and others we worked with at Google and other places, kind of taking programmatic ways of labeling data, and we said, okay, we just want to support that, right? So it always ends up being iterative. Putting that more on Rails so we can both support it better and analyze it better is something that we've done a lot of, but in different pieces. I actually have a project right now where we're working with someone at Stanford in Percy Lang's group who's working on, he does active learning theory. So we're thinking about, okay, what is the active learning version, probably similar to what you did, but more from the kind of theory perspective, what does that look like, right? Where traditional active learning, you're saying, okay, I want to find out what data point do I ask for a label for. Here we're saying, what set of points do I show to a user to get them to write a labeling function in the most sort of helpful part of the space. So yeah, I'd love to chat afterwards, but it's definitely, it's always iterative, and putting that more on Rails is just an ongoing bit of work. It ends up also being something that is very important on the engineering side. So when we actually go and productize this with partners who use it and bring it internally, like Google or Intel or others, a big part of that ends up being how you put that process on Rails, probably similar to what you worked on. Cool. So that was that section, and then the final section, I'll just give a little intuition about some of the interesting stuff here. This is for the database or data management folks in the room of the lineage, is a word that community likes, or we like. But a simple example just to illustrate that is, okay, well, imagine we have one set of labeling functions that label 1 million points, so they don't abstain that much, but at 60% accuracy. And then we have one set of points that label sort of 10,000 points at 90% accuracy. And we just dump these in and treat them identically. Well, then you could imagine that the average training label accuracy is barely better than 60%, right? The high quality, low coverage ones get diluted. So this is really frustrating if you are a user like I and other collaborators were of an early version of the system. You're dumping in more sort of really high accuracy sources, and your model performance is not budging. Right, so there's one little solution. We use basically probabilistic labels. And this is a really simple tweak to kind of integrate and pass on this quality knowledge or this lineage information to the final model. So here, for example, in standard empirical risk minimization, the details aren't important, but the basic idea is that, okay, we would have labels in our radiology problem that are just yes, no, just hard labels, normal or abnormal, right? And we would just count up on every iteration, how many mistakes did the model make, and just try to minimize that sum. Right? That's how you train models these days. And we just use a really simple tweak that we call noise-aware version of this, where we, instead of counting up the mistakes, we have a probabilistic label that says, okay, here's the confidence of it being normal or abnormal, and we take the expected number of mistakes and try to minimize that sum. So this is just a simple one-line tweak in TensorFlow or PyTorch that lets you pass on the lineage or quality of the labels to the model and circumvents that kind of frustrating wall that you'd hit otherwise. Awesome. Okay. So what I'm going to do in the remaining 5 minutes is I will mostly focus on Snorkel, and then I'm just going to flash some of the other projects. And the goal there really is just to, I'm happy to talk about them more in the office hours, really just to kind of give a sense of the diversity of things people do around training data and some efforts that we've been working on to support them. Briefly, I'll mention this. So I'll finish up on Snorkel, and then I'll spend just a minute or two breezing through just quick plugs for the other systems that you can look up later. So one question quickly is that often comes up here is, okay, we have this, this procedure, this fancy procedure to reweight and combine the labels, and then you get labels. Why not just use that, right? Why are we using the labels to train another model? And there could be settings where you would just stop there. The reasons are kind of twofold, though, in terms of broad buckets. One is that this model, meaning just any model you can download from the internet these days that may have some baked-in knowledge, is often can generalize beyond the labeling functions. Right? So I write a labeling function that says, look for the word malignant in the reports, and if so, label it bad. Often you can get a model that either has information baked in, like it knows about synonyms, and therefore can expand beyond the labeling functions, or it can just learn these co-occurring features from enough unlabeled data. That's where the theory bit comes in. And that's actually answering that question of what happens if all the labeling functions abstain? Well, often the biggest improvement we get with this model is actually just it covers more examples that the labeling functions don't. A second use case is what I call cross-modal transfer, where the labeling functions can be written over a different feature set than the final model. So I'll show that with an example. And this kind of this will be the thrilling conclusion of our running radiology example. So here, in this chest X-ray one, actually our radiologist really only wrote labeling functions over the text portion. But we trained a model over the image portion. So at test time, when we only had images and no blobs of text, the labeling functions are useless as a predictor, but the model we trained with them is actually very useful. This also crops up in industry, like we wrote about it in a recent publication we put out with Google around a couple of deployments there, where the labeling functions were written over one feature set that we called non-servable features, internal features to Google, but we trained a model over a different set of features that were servable in production. So this trick ends up being quite important in practice. And it's kind of using training data as a medium of transferring domain knowledge from one modality or set of features to another. Just to finish the punchline, this is a line, I just like this project. This is the ROC-AUC curve, the predicted performance after months of hand-labeled data for one of these X-ray problems. This is a recent publication from our collaborators in the radiology department at Stanford after years. Then they wrote 20 labeling functions over about 8 hours, roughly in aggregate. And this is what we get with Snorkel. So in one sense, this is kind of, call it eye-popping or embarrassing in that we really replaced person years of effort in hours. Another sense, it should seem like a very common sense result that you should be able to do something smarter than just labeling data points with single bit labels, right? You should be able to use all the information that's around them. That should seem like low-hanging fruit. And all that we do in Snorkel is just try to make a platform and a framework for getting that low-hanging fruit rather than doing these ridiculously long labeling efforts. And we've done this in medical monitoring with many different modalities. We've done a lot of work, and this is kind of what shows up online in our current version that's public there. More is this knowledge-based construction of using Snorkel to train models that pull information out of text or documents, and then a bunch of industry deployments, some of which are published about or are public. Briefly, I'll mention that as theory kind of pointed to, we actually get scaling. We dump in more unlabeled data, right? So you can write, say, 20 labeling functions, keep that constant, and you dump in more data, the performance gets better. So here, this was a problem over text. We went from a couple hundred documents to 63,000, but the same set of labeling functions got up 20 points in accuracy. And then finally, we asked the question, does this actually make it easier to use? So we set up a user study, a 2-day one. We had 15 teams come from across the US, and we saw that actually when we compared novice users who'd never used Snorkel before spend 2.5 hours writing labeling functions, the rest of the day learning about Snorkel, versus if we just paid people for 7 hours to label data, actually do about 50% better. So that's the high-level bit. Again, high-level sketches, we're trying to, rather than throwing out all this expert knowledge and data that's in a domain expert's head or in the organization or just accessible online and saying, okay, well now spend months labeling data to get access to the ML stack, we want to actually create that bridge. That's another way of viewing this. Okay, so I'll just briefly mention these other two. How am I on time? Probably bad.
Yeah, 2 minutes.
Okay, well, that's 1 minute per. So data augmentation, really simple idea, and it's often treated as a pre-processing step. Just, okay, well, if I have this is the MNIST handwritten digit classification task. I just want to classify 6s from 9s. Let me just rotate them a lot to teach the model about rotational invariance. Effectively, rather than baking it into the features, which I'm no longer, in the new deep learning style of things, defining myself. It turns out that actually, following the theme, doing this data augmentation amounts for an order of magnitude or more often in performance gains than actually what fancy model architecture you choose. Like the leaderboards are fighting over under a point. Using data augmentation versus not accounts for in CFAR 100, 13.4 points on average. The problem is that it's hard to tune, even though it's so critical. It's treated just as a pre-processing step. But the idea is that we can have users provide little incremental transformations and then figure out how to tune them automatically for new domains. And so rather than labeling functions, we now have transformation functions. I'll skip by the details there. We applied it over not just images, but text and also medical settings using a generative adversarial approach. And that's now in Google's auto-augment system, which got a new state-of-the-art recently, or a version of it. And then finally, I'll just give a brief pointer. This is online. We got a recent state-of-the-art with this. But this is Snorkel Metal, is a system, okay, say we don't just want to classify things as normal, as in most cases you don't just have one label you want to predict, but you actually have a bunch of related labels. We'd like to also be predicting, is there some kind of consolidation? Is there some type of pneumothorax? I have no idea what those mean, but they're bad, I guess. Anyway, our doctors care about these kinds of things for some reason. So, the interesting thing here is that these aren't just unrelated tasks. These are logically related. This is a toy example, but it's expressing a hierarchical subsumption. If one of these diseases is there, this also implies abnormal. So the simple question is, how do we approach modeling these multiple related tasks? This is picking up on an old lines of work in this weak supervision setting. So I'll skip over the, but again, the problem is, if we have multiple tasks, even if we're using something like Snorkel, we still have to write labeling functions for multiple tasks, but maybe if we handle them all together, we can do better with less. And that's all online, and I will conclude there. I had some next step stuff, but we'll have to come to another talk if you want to hear about that. Again, the key idea is that by adding just a little bit of mathematical and system structure around this emerging process of training data creation and management, we can radically accelerate it and make it much more flexible and usable. And so thanks to all of you for listening.